Okay, so we're going to start a new topic looking at circular motion, things going in a circle. So if it's travelling in a circle, you could actually look at its velocity at any point as being a tangent to the circle. And so you could draw things like that there, going off on a tangent. That one's a bit rough. And each of those would be a velocity. Okay, so the question becomes then, if this is going at a steady speed, is it accelerating or not? And the answer is it is accelerating, because acceleration is the rate of change of velocity. And even though the size or the magnitude of velocity is not changing, you can see that it's changing direction all the time. So because it's always changing direction, getting a change in direction for the velocity all the time, that's changing. Therefore, you've got a velocity that's changing. And because of that, you must be getting an acceleration, because acceleration is rate of change of velocity. And so as a logical thing, you've got direction that's changing. That means that the velocity is changing, and therefore it must be accelerating. And that means the force is needed, obviously, by the way, because of Newton's second law. So that's one way of looking at this. This is changing direction, and therefore the velocity must be changing. Therefore, you've got a change in velocity over a certain time. You're on acceleration, and therefore a force. And that force could be provided by lots of things. So things that are going in a circle need to have that force provided to stay in a circle. So if it was a car going around a corner, then we would be talking about the friction between the tyres and the road. If it was an atom where you've got an electron, which is negative, going around a positive nucleus, the force there is electrical force. If you were talking about an item on the end of a string and it's being swung around, then the string tension is providing the force towards push it there. And it turns out this force will be towards the centre. Now, you can actually argue this another way. If you look at it from Newton's law's point of view, according to Newton's first law, an object's velocity should stay the same unless a force is acting on it. So if it's this velocity is not staying the same, so therefore there must be a force acting. So velocity changes due to change in direction, because of a change in direction. And because of that, there must be a force acting, because Newton's first law says it should actually keep going in a straight line if there's no forces. Therefore, there must be forces. And if there's a force acting, it must be accelerating, because of F equals ma. So there's two weird ways of arguing that. And you can show that. I've got some notes here on this. So an object travelling on a circular path at a constant speed is accelerating. Why? First of all, it's constantly changing direction. That means its velocity is changing, because velocity is speed in a given direction. Therefore, it's always accelerating, since a is the rate of change of velocity, and therefore a force must be acting. But the second argument here is that, according to Newton's first law, object's velocity is constant if there's no forces. Here, the object's changing direction, so it hasn't got a constant velocity, it's changing. Therefore, there's a force. Therefore, it must be accelerating. So you can see these are very similar ideas, but one's based on using Newton's laws to explain it. One's based on the definition of what is velocity and what is acceleration. I've got that written out as a PowerPoint there as well from Mr. McGarry. Anything going in a circular motion is a velocity that's changing there because of a change in direction. Now, it turns out you can show that the acceleration then that's causing that change in velocity is at 90 degrees to the velocity at all times towards the centre of the circle. All right, and we've gone through those two arguments about one's a change in direction, so a change in velocity, so an acceleration. The second argument's all about the laws. It should have kept the same velocity according to the first law, but it's changing velocity and direction, so therefore there's a force, therefore there's an acceleration. Okay, and you can actually show the change in velocity there and look at the acceleration there. So if you consider two positions here, this position one where the velocity is at a tangent vi or v1, and then a time t seconds later it's gone through a certain path here, and it's now at a different velocity, slightly different position. You could actually do a vector subtraction here to show what the change in velocity is between these 2 points. Okay, delta v is vf minus vi, or v2 minus v1, and with that there you would have your vi and your vf. The vf is the first one, so your first vector is vf. Now, to do minus vi, we want to add the thing in the tip to tail in the opposite direction to vi. So this is your vf minus your vi, and you get your change in velocity there. And you can see that change in velocity there, halfway between the 2 points, which is where the average change in velocity would be, it is towards the centre. And obviously, if the change in velocity is towards the centre, the acceleration needs to be towards the centre, because a is delta v on t. Now, the smaller you make that time interval, the closer the average velocity and change in velocity and acceleration gets to the instantaneous one. For a very small time interval, you'll find the average velocity and average change in velocity and average acceleration will become equal to the instantaneous one. There's a cheats way of working this out, which is much easier. You can actually use a formula of this, that the acceleration of anything going in a circle there, called the centripetal acceleration, or the acceleration towards the centre of the circle, is given by the velocity squared divided by the radius. So put in the speed that you know, square it, and divide by the radius of the path. So you can do some simple examples of this. If you've been given a radius of 10 centimetres or 0.10 metres at a speed of 10 metres a second versus a speed of 20, is the centripetal acceleration needed to do these changes the same? If you use your cheat formula there that's on the formula sheet, it's just 10 squared divided by 0.1, I should say 0.10, and you get an acceleration there, and you should round that off to two significant figures, but it's 1,000 metres per second squared, whereas here it's 4,000 because the speed is twice as big. You will find you'll get 4 times the acceleration, because acceleration is proportional to the speed squared. Now, some other things to bear in mind here. So we have got a cheats way of working out acceleration as v squared over r. Sometimes you won't be told the velocity, you'll have to work it out. So if you're told the radius of a circle, let's say it was 100 metres, and you're told that the object, it might be a car going around that circle, is doing that 100 metres as a full circle, and it completes a lap every, say, 30 seconds, can you find the v for that? All right, so that you can go and work out the acceleration. Well, velocity is actually the distance travelled over the time. All right, so the total distance travelled around that circle, if it just does one lap, the circumference of a circle is 2 pi r or pi d, and the time for one lap is called the period t. So in this case, we've got 2 pi r over. Now, the 2 pi r is 100. Sometimes they'll tell you the diameter, so be careful to make sure you halve it. But you want the radius. That's the total distance travelled around the circle, and it's taking a time of 30 seconds. So make sure it's in metres and in seconds, and that will tell you the velocity there in metres per second. And it's sometimes called the tangential velocity or linear velocity, or just the velocity or the magnitude of velocity, but it tells you the size of the velocity that's going around that circle, even though the direction is changing. So looking at that, you see a value of 20.9 metres per second. So when you want the acceleration then of that object, you're going to do v squared over r. You're going to do 20.9 squared divided by your radius there of 100 metres, and you'll get an acceleration in metres per second squared. Sorry, 4.39. So 4.39 metres per second squared, and that's towards the centre, because I just said that before, that it's always towards the centre. So the velocity is that way. The acceleration is always at 90 degrees to that. Well, that's not a very good 90-degree dial. Okay. You can therefore work out the force, F equals ma, using Newton's second law, if you know the mass of the car. There's another way you can do it straight away, if you want to bypass it and do it in one step. F equals ma is equal to m. Now the a is v squared over r, so you could just use that formula all the time if you want to work out the force of an object going in a circle. Now, you could be given some questions where they're asking to explain what's going on here. One of the things here could be explain why the force that causes an object to move in a circle does not change the speed of the object, but it changes its velocity. So you're being asked to explain here, why is this force that's causing it to go in a circle not change the speed, the size of the velocity, but it changes the velocity. So you need to think about, why does it only change the direction? Sorry, the force is always at 90 degrees to the velocity, always. Now that means at no time do you end up with the force, any component of the force, in the same direction as the velocity, because if it did, there'd be a force component going the same way as the velocity, and if you had a force component going the same way as the velocity, it'd increase the size of the velocity. But the fact that the force is always 90 to the velocity, like that, means that there's no force component in that same direction, so the velocity doesn't get any bigger. Okay, so key things to point out there is that the force is always at 90 degrees to the velocity, or right angles to it. This means the size does not change, and therefore the speed doesn't change. Okay, because no component of the force ever acts in that same direction as the velocity. So that's just something to bear in mind. But the force does cause a change in direction. Okay, and so that's why the velocity changes. Now, other questions you could get are things like this, where they're a bit more complicated. A mass of 2.5 kilograms is swung on the end of a string. The the radius is 80 centimetres and the string has a braking tension of 50 newtons. What is the maximum possible speed before the string breaks? So you need to look at what you've got here, and if you look at it, you've got a mass, you've got a radius there, you have been told the braking tension. Now don't forget, tension is a type of force. It's one of the forces that can cause circular motion. So you've got gravity, you've got tension, we've got electric force for atoms and stuff, and you've also got friction for cars going around the road. So they're the key ones we know about. So we know those, and it's saying what's the maximum possible speed. In this case, we use velocity here. So is there a formula where we've got those three that we know, and we want to find v? So the one to use is probably this F equals ma, but if you substitute it, F equals mv squared over r, we'll have all the bits we need. So if we look at that then, F equals ma, you can put in your a equals e squared over r there, so start with that one. We've got all these knowns on the side there. So you could rearrange this first in one go by bringing the divide by r up to times by f. Instead of times by m, you divide by m, and then you would square root it. So doing that would give you the formula in one go. It's okay to substitute the numbers and rearrange afterwards, but you end up with about 4 meters per second there. So that's as fast as you could go before the string would actually break. Now lastly, you might be asked to do questions about proportionality here, which everyone hates apparently. So if you've got a car going around here at a fixed velocity there on a fixed track of the same radius with the same mass and whatever else, you could be asked what would happen to the force if we doubled the speed of that car. So the two quantities we're focusing on here, what's going to happen to the force if we change speed? So you need to look at a formula that will link force and speed, or force and velocity together. Now if you think about it, that's the one we're going to use. Now from that you should be able to see that force is proportional to the velocity squared. So if you follow that, you should be able to see that force is proportional to the velocity squared, and I would highlight that and then talk about what the velocity is going to do. So in this case, the velocity is going to double. So the fact that it's 2 times by v means that 2 squared would give you 4 times the force, because it's obviously a square factor there. So 2 squared is 4. If it was 3 times as fast, you would get 9 times the force. There's other questions you could be asked there. What would happen if you actually did a quarter of the velocity and a half the radius then? So that's a bit more complicated. On the count of the velocity then, if you quartered the velocity, if you square that, you will get only a 16th of the original force based on that square factor. But you've got to remember, you're now halving the radius. And if you make the radius smaller here, f is inversely proportional to r. A smaller radius, say 2 times smaller, or half the size, is going to give you 2 times bigger the f. So we're going to get 2f as one focus, 16f as the other, 1/16. Altogether, 1/16 times by 2, you're going to get 1/8 of the force. So you can get tricky ones like that as well. Okay? So it's 1/16 on the count of velocity squared, but it's 2 times bigger on the count of the half the radius, because it's an inverse. That gives you an 1/8. They might ask you about what's going to happen to the force if you change, the acceleration if you change the mass. So in this case here, if we have one like this similar sort of question there, what would happen to the acceleration of the object if we did twice the velocity? Well, the same thing's going to happen. Okay, you're going to get 2 squared, 4. But what would happen to the acceleration if you doubled the mass of the car? Well, the answer is nothing, because mass is not going to affect the acceleration. So therefore, doubling the mass would have no effect. It would have an effect if I asked the same question and said, what would happen to the force needed to go around the corner if I doubled the mass? In that case, the force would have to double, because they're proportional to each other. Okay, thanks.